Hello friends, I am Dr. Neeraj Upadhyay. Hope you remember in the last module you learned about the approach of crystal field theory for understanding formation of low spin and high spin complexes. There you get to know that pairing energy and the crystal field splitting energy are the energies working opposite to each other. For your information, Hunds will suggest all degenerate orbitals in ground state feel singly and unidirectional first, and then only pairing can start. This is because degenerate orbital system exchange its energy electron from one orbital to other. More the equivalent exchanges, more energy are released by the system. The released energy is called exchange energy. Also, during pairing of electrons in an orbital, electronic repulsion takes place, and to overcome this electronic repulsion, system needs to provide an additional amount of energy called pairing energy P. So, by pairing of electrons, energy of orbital system increases. But in a crystal field environment, degeneracy of d orbital breaks. For example, in octahedral system, it breaks into T2g and Eg set of orbitals. The energy gap between T2g and Eg set of orbital is called crystal field splitting energy. Thus, to fill electrons in Eg set of orbital, system needs an energy equal to crystal field splitting energy, which is called delta O. Formation of low spin and high spin complex is a result of competition between delta O and P. If delta O is greater than P, a low spin complex results, and vice versa. The configuration D1, D2, D3, D8, D9 and D10 are having similar electronic arrangement in both the low spin and high spin configuration. The value of crystal field stabilization energy for low spin configuration in D4, D5, D6 and D7 arrangement is found more than that of the CFSE value for corresponding high spin complexes. Since the value of pairing energy in split and unsplit state remains almost same, it is only the value of delta O which decides about formation of low spin or high spin complexes. But what are the deciding factor for the value of delta O? How can you obtain the value of delta O and compare with the pairing energy? Here in this module, we will discuss about the factors that affect crystal field splitting energy. Before proceeding to factors affecting crystal field splitting energy, let's first learn about some quantitative aspects of pairing energy. So, let's talk about the magnitude of pairing energy. Here is a list of value of pairing energy P for oxygen state +2 and +3 in your screen. In this table, you can analyze that the value of pairing energy in D5 configuration is maximum. Similarly, you can see value of pairing energy for chromium ion is more than that of the value of pairing energy for iron ion. This is because the iron ion contains a pair of electron, and because of this pairing, the electronic repulsion increases, which in result increases the orbital energy of the system. Also, the value of pairing energy increases with increase in oxidation state of the metal ion. With increase in more pair of electrons, pairing energy increases, and this decreases the stability and therefore attractive forces between nucleus and electron. Here I want to remind you, in module 2 you have learnt about the concept of atomic radii. There, atomic radii of transition metals was decreasing when you go left to right in a period. From scandium to manganese, the radii was decreasing. This is because of gained stability by increase in exchange energy. But after manganese, decrease in size stops. Iron, cobalt and nickel has merely any change in their radii, and then size of copper and zinc increases. Here you can't ignore one of the cause of increase of radii as pairing energy. With increase in pairing energy, stability of atom decreases, which results increase in size of atoms or ion. Now, let's talk about the factors that can affect the crystal field splitting energy. value of pairing energy is almost fixed in free or even after surrounding of the ligands in split or unsplit state of d orbitals. So, formation of low spin and high spin complex depends on the value of delta. A complex system is formed by metal ions and ligand. So, obviously, we should find the clue in these terms only. So, keeping all the other parameters fixed, effects of single parameter can be evaluated. The first parameter that I want to talk about, nature of ligand. Ligand is the species which, according to crystal field theory, bring negative charge density in front of metal d orbitals. So, the first factor that can affect crystal field splitting is the type of ligand. So, keeping metal ion fixed, a number of experimentations were done to evaluate effect of different types of ligand on crystal field splitting. The order obtained for some of the ligands are summarized and which is shown in your screen. Here, the ligands are arranged in order to produce increasing value of crystal field splitting energy with a fixed metal ion. This series is known as spectrochemical series. The ligand which produces less splitting like iodide ion, bromide ion, chloride ion, fluoride ion, etc. are called weak ligands. The ligands that produce significant crystal field splitting but not enough to cross the pairing energy like water, oxalate, OH- etc. are called moderately weak ligands. The ligands that produces sufficient energy to overcome the pairing energy in general are called moderately strong ligand. The example of such ligands are N-donor of thiocyanate, pyridine, ammonia, etc. While the ligands that produce enough energy to overcome with pairing energy like PR3, Cn-, NO+, CO, etc. are called strong ligands. The value of crystal field splitting obtained from absorption spectra for some of the ligands with Cr3 plus ion in octahedral geometry is shown here on your screen. So, from the data like this, you can conclude that Cl- is a weak ligand, OH2 ligand is a moderately weak, ammonia is moderately strong, and Cn- ion is a strong ligand. In influence of the strong ligand, molecule forms low spin complex. It is therefore a low spin complex is also called a strong field complex and vice versa. Thus, crystal field theory was successful to provide qualitative and quantitative picture behind strength of the ligand, but it was never comfortable with its output. For example, iodide ion being a negatively charged ligand should produce more electrostatic repulsion than neutral molecule like CO. Similarly, electronegativity, dipole moment and size of ligand should play significant role in crystal field splitting. But this is hard to see in the spectrochemical series. For example, OH- is a weaker ligand compared to H2O. Ammonia is a stronger ligand than water. Though the dipole moment of water is higher than that of ammonia. No convincing reason was here with crystal field theory for explaining order of experimentally obtained spectrochemical series. Later molecular orbital theory explained these, but this is not the part of our syllabus. Now, the second factor that I want to discuss you about, the effect of charge or oxidation state of central metal ion. Higher the positive charge on the central metal ion, more attraction will be felt by ligand, which in consequence increases the crystal field splitting. I mean, when ligands are approaching closer to the metal, the splitting between d orbital will be larger. Here in the crystal field splitting of first transition series, metal aqua complexes for oxidation state +2 and +3 of different metal ions are shown. In most of the cases, as shown in your table, increase in magnitude of crystal field splitting in the aqua complex of first transition series, metal ion between their oxidation state +2 to +3, it increases by 20% to 30%, but become exceptionally very high in case of manganese. This is because of extra stability of D5 configuration of manganese second ion. In some other cases, increase in crystal field splitting between +2 to +3 oxidation state of metal complexes is increased by 50% to 100%. For example, in the case cobalt, the crystal field splitting for COH2O6 plus is 122 kJ per mole, which increases to 272 kJ per mole for cobalt for hexaaqua cobalt third ion. It is therefore with moderately strong ligand metal in +3 oxidation state mostly prefer formation of low spin complex. Now let's talk about the nature of metal ion. There is significant role of size of metal ion on crystal field splitting. Larger the size of metal ion, more their orbital have influence with the external field of the ligand, which results higher value of crystal field splitting energy. Generally, going down the group of transition series, crystal field splitting increases by 30% to 50% when the same configuration and same oxidation state is involved. Some value of crystal field splitting energy is given here in the table on your screen. In some cases, splitting increases by 100% in going down the group. As a result of this high crystal field splitting, it is observed that in almost all the complexes of second and third transition series form low spin complexes. Now let's talk about the geometry of the complexes. Geometry of complex also affect the value of crystal field splitting energy. The crystal field splitting by the same ligand with the same metal ion configuration for tetrahedral arrangement is almost 45% of the value of the crystal field splitting in octahedral arrangement. A square planar arrangement has crystal field splitting in between tetrahedral and octahedral arrangement. It is therefore molecule in tetrahedral arrangement almost every time form high spin complex. Now we have learnt almost all the concept required for determining the crystal field stabilization energy. So let's solve a numerical problem. In this problem, you have a complex COX63- where X is a monodentate uninegative ligand. Now you calculate the CFSC value for part A. Value of crystal field splitting energy is 15,000 centimeter inverse and that of pairing energy is 18,000 centimeter inverse. Then calculate the value of CFSC in this case. Case B, value of crystal field splitting energy is 21,000 centimeter inverse and value of pairing energy is 18,000 centimeter inverse. So in that case too, you determine the value of CFSC. The problem starts with the information that the molecule COX63- contain a ligand X, which is monodentate and uninegative. So oxidation state of X is -1. Cobalt is the central metal ion and let its oxidation state is N. Since overall the molecular ion has -3 charge, which indicate the overall charge of the complex. So the algebraic sum of all the charges should be equal to -3. I mean N plus 6 into -1 should be equal to -3. Therefore, value of N should be +3. That is, the oxidation state of cobalt came here is +3. The electronic configuration of cobalt in its natural state or neutral state is 3d74s2. So after removal of 3 electron, that is in the oxidation state +3 of cobalt, the electronic configuration would be 3d6. Now in octahedral arrangement of 6x ligand, the 5 degenerate set of d orbital break into 2 sets of orbitals, that is T2g and Eg set of orbitals. So now discuss the case A. Here value of pairing energy is given as 18,000 centimeter inverse, which is higher than the value of crystal field splitting energy, which was given 15,000 centimeter inverse. So this complex will form a high spin arrangement. On filling electrons, the configuration will become T2g4 Eg2. In this case, total number of paired orbital is equal to 1. Before crystal field splitting, the number of paired orbital is equal to 1. So there would be no net change in the value of pairing energy. Also, since each electron of T2g level is in octahedral geometry and is stabilized by minus 0.4 delta O, and each electron present in Eg cell is destabilized by plus 0.6 delta O. Therefore, crystal field stabilization energy would become 4 into minus 0.4 delta O plus 2 into plus 0.6 delta O. That will become minus 0.40 delta O, and the value of delta O is 15,000 centimeter inverse. That is, the CFSE value would be minus 0.4 into 15,000 equal to 6,000 centimeter inverse, and when you convert centimeter inverse into kilojoule per mole, the value will become 71.68 kilojoule per mole. Now, let us discuss the case B, where it was given that the crystal field splitting value is 24,000 centimeter inverse, and this value is higher than the value of pairing energy, which is given as 18,000 centimeter inverse. So, here the formed complex would be low spin. It is therefore, the electronic arrangement in the splitted form or d orbital would be T2G6 Eg0. So, the paired orbital is 3, while in d6 arrangement without splitting, d orbital was containing only one pair of electron. So, the loss of stability due to pairing energy is equal to 3p minus p equal to 2p. Calculating the value of CFSE now is 6 into minus 0.4 delta O is plus 2p is equal to minus 2.4 delta O plus 2p. Putting the value of delta O and p in this equation, CFSE would become minus 2.4 into 24,000 plus 2 into 18,000 is equal to minus 21,600 centimeter inverse. That can be converted into kilojoule per mole, and the value will become 258 kilojoule per mole. Now, I have a question for you. Comment whether CONH3 plus should be a low spin or a high spin complex. Here, ammonia is a moderately strong ligand, which indicate to provide nearby crystal field splitting energy to the pairing energy that may or may not be sufficient to frame a low spin complex. Looking to the central metal ion, cobalt is an element of first transition series, which in general form both that is low spin and high spin complex. Cobalt itself has two most abundant oxidation state, plus 2 and plus 3. Here in our given example, cobalt is in plus 3 oxidation state, that is in higher oxidation state. You have just learned that with increase of oxidation state, crystal field splitting energy increases. So, counting all these factors together, you can estimate that this complex is a low spin complex, and the splitting would be like T2G6 Eg0. The competition between pairing energy and crystal field splitting energy decides formation of high spin or low spin complex. The complex having higher value of crystal field splitting compared to pairing energy form a low spin complex, and vice versa. At one side, where pairing energy of metallic ion has almost a fixed value, crystal field splitting energy depends on many factors. These factors are originated from the structure of the molecule itself. The effect of ligand on crystal field splitting was summarized by framing a spectrochemical series, where strength of ligand increases on going left to right. Now, the theory suggests the increasing strength of the ligand, but theoretically there were many objections that crystal field theory was unable to answer. The crystal field splitting was found to be increased with change in oxidation state of the metal ion. Nature of metal ion also affect the crystal field splitting energy. By going down in a group, crystal field splitting was found to be increased by 30 to 50% of the value of crystal field splitting of the first transition series. It is therefore, in most of the cases, elements of second and third transition series prefer to form low spin complex. Finally, geometry of the complex have also found to have significant effect. An octahedral arrangement has higher crystal field splitting followed by a square planar, which in turn has higher splitting than a tetrahedral arrangement. Thank you very much for listening this video.